So I'm going to show you the lab we did, or the demonstration I led today in class, and it involved looking at finding our percent error of our calculations. And we were comparing an experimental value in which we dropped an object in the stairwell to the theoretical value of time it should have taken for an object to fall. So we're going to take this equation here. So our percent error is going to equal the experimental value minus the theoretical value divided by the theoretical value times 100. And we're going to get a value here. This is going to be a percentage. Percent is going to be our percent error. So here's what we did. So let's re-simulate this. We were in the stairwell and we dropped an object off of, say, 5 meters, right? This was the hand railing. So we dropped this off here. I'm standing here and I dropped this object and it's going to fall 5 meters. Boom. So the height in which it fell was 5 meters. So in class right now we're learning how to do calculations involving free fall. And we know that an object that is in free fall is being affected only by gravity, and it is accelerating towards the earth at 10 meters per second, or 10 meters per second squared. So that means this ball that we dropped at exactly 5 meters, in theory, we can calculate the time it should take. So I've got d of y equals 1/2 gt squared. And we know we're talking 1/2 of g on Earth. So we've simplified this as d of y equals 5t squared. So this is what we're working with. And here's what we can calculate. We can come up with the theoretical value of t, right? The time in which it takes to fall 5 meters. Here's my d of y divided by 5, right? I'm isolating t. And it would be the square root of 5 divided by 5, which is the square root of 1, which equals 1 second. In theory, right, theoretical value, in theory, it should take 1 second for an object to fall 5 meters, right? That's what we're solving here. This is what we're looking at. D of y, the distance at which it fell in the y direction, vertically, it fell 5 meters. So then we went out and timed it. And we had class times that were all over the map, and I'm not overly concerned about what those times were. So I'm going to give you some scenario here. Let's say that we came up with an average time. Let's say we had a 0.94, and another student timed it to be 0.90, and another student timed it to be 0.86. And let's say that we came up with an average of 0.90 seconds to fall 5 meters. Well, you'll see that when we time it ourselves, we're not that good at timing. I mean, it's not the biggest deal. We use technology to do it. But we timed it manually, and we were off. And we can actually calculate our percent error, right? Our experimental error, by comparing our experimental time to the theoretical time. And I can do this, and I can plug in these numbers, and I'm gonna do that for you right here, right now. I know my experimental time, right? My experiment is the number we got, the 0.9 seconds. Minus the theoretical time, let's call it theory, is 1 second, divided by 1 second, right? Times 100. Gives us a percentage here of, let's see, 0.9 minus 1 is negative 0.1 divided by 1 is 0.1 times 100 tells me it was negative 10%. You might say, well, what does negative 10% mean? Well, our experimental error, we were 10% off. Our value was 10% below the theoretical value. Right? So the negative actually means we were below it. If this number here happened to be greater than 1 second, we would have a positive number because my experimental value would be greater than the theoretical value. So this would be positive. So the plus and the minus here means if you're above or below the actual value. Right? So if I gave you a hypothetical scenario, which I will do a second one, let's say we had 3 trials and say it was 1.02, 1.08, and we'll go with an easy one here, 1.4. Therefore, our average here would be 1.08. So this would be my experimental time. So if I took, so this would be in seconds. So I'm re-simulating this time to fall. It's just example class data. This is not anything anybody took. So if these were our class trials, and we find our average of 1.08 seconds, I'm going to use the same idea here. Notice I'm just going to write next to it. Our experimental value was 1.08. The theoretical value is 1.0, right? These are seconds to fall 5 meters. Divided by 1 second, right? Still 1 second to fall the 5 meters, right? This is our theoretical value here. So this will be positive 0.08 times 100 would be 8 It's an implied positive. This would imply that our percent error, we were 8%. Oops, that's supposed to be above. We were 8% above the theoretical value, right? The theoretical value was 1 second. So this 8%, our value here of time, we were over the actual theoretical value. In this case here, we were below by 10%. So I just want you to realize that the numbers we calculate in class, we can actually determine our percent error here. So the second part of class that we did, I'm going to leave this kind of available for you to see because we're still using this, but we're doing it a little differently. We dropped a a rubber bouncy ball and a golf ball in class. So we dropped two different objects. We dropped two items and we dropped them from 5 meters. So let's redo this one. Boom, 5 meters. And when so we were standing up here, here's that railing, here's me, and I dropped them. So they fell 5 meters, boom. And they hit the ground, boom. And then they bounce back up. And they bounce back up to some distance. And this distance in which they rebound to, so let's call this a rebound height. The rebound height was never the height at which I dropped it from. Remember, I dropped it from 5 meters. That's the initial conditions, that's the starting height. But let's say it only rebounded to, say, 3.5 meters. Well, hopefully you realize that the scenario is a little different. Our experimental value and our theoretical values are a little different scenario here. We're talking about the rebound height for the experimental value, meaning what did we measure it to rebound back to? And the theoretical value is if it was a perfect system with no friction, right? No friction in this little collision with the floor here, it should bounce back up to 5 meters, but it did not. And we even witnessed that it did not bounce up to 5 meters. It bounced to some lower value, right? So the rebound height was only 3.5 meters, right? That's how the measure we're going to work from. So I'm going to use this equation here. Our experimental value was 3.5 meters. And the theoretical height that we dropped it from was 5 meters. We divide this by 5 meters, and we multiply this times 100. And you'll find that our value was negative 30%. So 3.5 minus 5 is a negative 1.5 divided by 5. We times 100, we get negative 0.30, or negative 30. Well, negative 0.3 times 100 is 30%. This is the key here. This is what I want you paying attention to. This negative value has meaning. It's very meaningful. And I'm going to use the term just for a second. It implies that it lost some of its energy. So when we talk about this here, and I'm going to write another color, and I want to make sure we get the physics of what's going on here. We're talking about energy. And the energy of this location right here, at location X, is all potential energy. It's all PE. So the energy here at the beginning is all potential energy. The energy the instant before it impacts the floor is all kinetic energy. Right? It's simply as it falls, it's speeding up, it's speeding up, it's speeding up, boom, until right here, the instant before it hits. It's all kinetic energy. That the potential energy was transformed into kinetic energy. But it's saying this, that energy is always conserved. In other words, the sum of the energy in, so my energy in, right, in the form of PE, must equal the sum of my energy out. In this case here, you might say, well, okay, if I drop it here from 5 meters and it rebounds only to 3.5, what happened here? Something happened here that we didn't get out of it. We didn't get out what was put in. So therefore, are we in violation of our concept of our conservation of energy? And no, we're not. Because at this point of contact right here on the rebound bounce, we have forms of friction that kind of surface here. They come out. And the forms of friction that we can kind of visualize, we can actually see, we can see and hear. We actually hear sound. Sound is a form of energy. In this collision, some of that rebounding energy was kind of, I don't want to keep using the term lost. It was simply transformed. It was transformed into new forms. And the new forms are what we're going over right now. These new forms are very, very significant. This is transformed into sound. There would have been some heat, although we don't have the measuring tools to measure it. and it would have also led to vibrations. That all total, the total heat in, or the total energy in always is conserved. So total energy in equals the total energy out. And you might say, well, how do we get this? Well, here's what we're saying. That my total energy in, this is supposed to be a sum of my energy in, is going to equal my sum total energy out. So my energy in is simply going to be the total potential energy here at the beginning. And you might say my we'll call it PE total at the beginning is going to equal my total potential energy after the collision, right? Collision with the floor, plus all of those forms of friction, right? Including the sound, the heat, and the vibrations. That the conservation of energy says you never get something for nothing. That if there's energy in the system, it has to go somewhere. It's not just lost. So this term lost is actually misleading, but I want you to see that the missing energy that is not accounted for in the rebound height is very much accounted for in these forms of friction when it collided with the floor. So when we bounce something, it's never going to rebound back to the original height, because the energy it gets transformed into new forms. And those new forms are, we can hear the sound. We'd need some very, very sensitive measuring tools to measure the heat, but we can feel the vibrations. So we can hear the sound, feel the vibrations, and you'll just have to kind of trust me on the heat piece. Total energy in must equal this total energy out. My total potential energy here is fully accounted for in this new potential energy of where it bounces to. Only this difference of height from here to here is represented by these forms of friction. And therefore it is all accounted for. Energy in equals energy out. I hope that makes sense of the lab activity we did today in class, or the demo that I led.